So in this lecture, we will start with introduction to neural networks. So if you recall the case of binary logistic regression, we had a single layer network. So in this case, we had an input layer where the input data vector was of the form x0, x1 up to xd. There was a weight multiplying each of the inputs. We're summing it up. So we're producing a weighted sum of the input vector and passing it through a sigmoid function. And phi of s was e to the s over 1 plus e to the s. And the idea was to assign probability of the label being +1 or -1 using the sigmoid function. Now neural networks are multi-layer networks. So instead of a single layer, here there is the input layer and an output layer and just one layer of weights. We will have multiple layers of weights. So here the idea is we still have an input layer we pass it through an intermediate layer called the hidden layer. So there is a set of nodes here with some nonlinear function theta, and there is a bipartite graph connecting the input nodes to each node in the hidden layer. And there are weights here on the hidden layer. So the output of the hidden nodes are denoted by H symbol. This is H1 up to Hn. So there are n nodes in the hidden layer, and then these can get connected to an output layer. So this is the output layer. So H1 is the output of hidden node 1, H2 is the output of hidden node 2, and so on. You'll have weights V1, V2, and up to Vn. There is also a bias node in the hidden layer that has no inputs but produces an output of 1. You multiply it by V0, you pass it through some other function, and you get the output Y. So again, in this is an example of a two-layer network. There is an input layer, then there is a set of edges connecting the input layer to nodes in the hidden layer. The hidden layer has n nodes in this example, and there are the weights between the input layer and the hidden units are denoted using the symbol W. So in this case, this weight here will be W11, this weight will be W21, and so on. So the weight between the ith node in the input layer and the jth node at the hidden layer is denoted by Wij. So this weight here will be WD1, this will be WD2, and so on. So this is the architecture of a two-layer network. Here there are two layers because there is a set of weights in the bipartite graph between the input layer and the hidden layer, and another set of weights between the hidden layer and the output layer. That's why it's a two-layer network. It's a number of layers of weights that are used. This can be extended to multi-layer by adding additional hidden layers and then connecting them using a bipartite graph. In this particular representation, theta and phi are nonlinear functions in general. So the interpretation here is that Wij is the weight between input node I and hidden layer node J. Okay. Vi is the weight on the edge between hidden layer node I and the output node. So the output of Hj is the output of node J in hidden layer. And so we can represent Hj as theta of W0j plus the summation of I going from 1 to D of Wij times xi. So the idea here is that if you go to one particular value H2, which is the output of the second node in the hidden layer, it is obtained by taking a weighted sum of all the incoming edges onto that node. So the first edge is this one. This is W12. It will be the weight on this edge. And we have the input is x0 equals, sorry, this will be W02. The input is x0 equals 1. This one here will be W12 and so on. And we'll take the weighted sum of all the edges. So you multiply the input value with the value of the weight, take the sum, and then apply this nonlinear function theta to it. So this is how the relationship works. Now, once we do that, so what is theta? Theta traditionally is taken as the following function. This is known as the hyperbolic tangent. It is a function that takes the input argument to be any real number. So this is S and this is theta of S, and it fluctuates between +1 and -1. So this is the asymptote for +1, this is the asymptote for -1, and it looks like this. So when S is very large, it will saturate to +1. When S is very large and negative, it saturates to -1. At 0, it is 0. The advantage of this function is that first it is bounded. So very large values of input will not overly dominate the network. So you want the outputs from each neuron to be bounded. It's also nearly linear around the origin. So theta of S is approximately S when S is small. So in this case, so when the input values are small, the function is approximately linear. It is zero-centered. So there is no bias introduced by this particular function. and this is advantageous so that negative values and positive values are treated equally. Uh, Also, its derivative is easy, it's differentiable everywhere, and the derivative can be just written like this. You can verify it. The derivative of theta with respect to s is 1 minus theta square of s. And so those are the main advantages. This is not the only function. There are other functions such as the ReLU function, theta of s is the max of 0 and s. So this is again a nonlinear function where the input is just set to 0 if the argument is negative, and it is taken to equal the input if it is positive. Surprisingly, this works very well in practice as well, and in a lot of current implementations, the hyperbolic tangent has been replaced by this ReLU function. However, in all historical papers and textbooks, you will see the tan h as the default function, and so in most of our discussion we will use this one. But in recent networks, people have found the ReLU function to surprisingly work well as well. So this is what we do. We take the input values, we compute a weighted sum by the weights on the edges, and then we compute hj as shown by this formula. We apply the nonlinear function theta, which we'll take it as the hyperbolic tangent, and then we'll compute hj. So this is how the output of each hidden node is generated. Now the output at value of the network y is obtained in a similar fashion. It's phi of v0 plus the summation of j going from 1 to n vj times hj. So we take just the weighted sum of all the values that are incident onto the hidden node here. So we have v0 plus v1h1 plus v2h2 and so on, and then we apply the function phi. Now the choice of phi depends on the application. If it is logistic regression, phi will be the sigmoid function. In linear regression, phi will be just a linear function, and so on. Okay, so the choice of phi will depend on the application, and we will not explicitly specify it. So the idea here is that once we have an input x, we use a two-step process to compute y, the output y. Step 1 is to apply nonlinear transformation hj is theta of w transpose xj, or the other way, hj is wj transpose x for j equals 1 to up to n. So the weight vector is multiplied with the input vector, and then we apply the nonlinear transformation at each hidden node. And then we apply linear model. So logistic regression, depending on the application, it could be linear regression to the resulting values to generate the output. So this may look a lot like, this resembles something we studied in chapter 3. So this resembles the nonlinear transformation approach in chapter 3. However, so for example, for quadratic transformation, if our input was x, we would apply z to be 1, x1, x2, x1 square, x2 square, x1, x2, and then apply linear model onto the z vector. Right? We studied this before. But there is a crucial difference when we do neural networks versus this traditional approach. And the difference is that the weight vectors wj are not fixed upfront. They are actually learned from the data itself. So neural networks are different from this approach because in this computation, the weights wi are not fixed a priori. They are learned using the training data. So in other words, neural networks correspond to automatic feature extraction, while the fixed nonlinearities correspond to the standard feature extraction. And so in this sense, neural networks are a lot more powerful than the previous approaches for nonlinear transformation that we studied. So this was really evident in the 2013 ImageNet challenge, which we discussed in the first week of the classes. Before to 2013, all the methods for doing image classification involved extracting some features from the image using some domain knowledge, like taking the DCT coefficients, keeping the high frequency signals, and so on, and then applying linear models to these fixed features. The use of convolutional neural networks was a big breakthrough because the features were not fixed beforehand, but they were learned from the data itself. And that got a significant improvement in performance than traditional methods. So this concept that the weight vectors are learned using the training data itself is actually a fundamental difference between neural networks and traditional methods. Another comment: what if the function theta is just the identity function? So we do not apply nonlinearity at hidden nodes. In this case, you can easily see that the overall system just becomes a linear model. So recall that y is given by phi of v0 plus summation of j equals 1 to n of Vj times Hj. Hj is theta of Wj transpose times x. So this is what the function is. Now if theta is an identity function, this is just phi of V0 plus summation of j going from 1 to n Vj Wj transpose times x. So this is just phi of Vj plus summation, or we can just write this as, if we take x outside the summation, then this is W effective transpose times x, where W effective is the summation of j going from 1 to n Vj times Wj. So this is just the standard logistic regression, for example. So in absence of the nonlinear transformation, adding the intermediate layer in the neural network does not change the model. It is still overall a standard linear model. Thus, adding a nonlinear function, a nonlinear transformation at each hidden node in the network is extremely important in order to get a nonlinear system overall. So let's do an example next to see how neural networks can be used to implement nonlinear decision boundaries. So we'll do an example where we have a training set with 4 points, and our input vector H will have entries which are either -1 or +1. So it will be a two-dimensional vector where each entry is -1 or +1. Normally we use the symbol X for the input data vector, but for reasons that will be clear soon, I'm using the symbol H for the input data vector. And we'll consider 3 different sets. The first set has 4 points, where the training set looks like this. You have points at -1 and +1. So you have these 4 points, and the label is as follows. You have pluses at 3 points. You have a plus here, you have a plus here, a plus here, and a minus here. So this is our first training set. Let's call this D1. So this function mathematically is the OR function. The output Y1 is the OR of the two input values H1 and H2. So this is the first coordinate, this is the second coordinate, and the label that we assign to each point is the OR of H1 and H2. So if one of the coordinates is plus, the output is plus. If both of them are minus, then the output is a minus. The set D2 will be what is called the AND function. So here we will have a plus only if both the labels are positive, and we'll have a minus everywhere else. So the second label is generated by the AND function. This is the ground truth for the two labels. The third data set is a function, again, where the input labels are plus or minus 1, or the input vector has two coordinates with entries either +1 or -1, and the label is minus if H1 is not equal to H2 and plus if H1 equals H2. So this is what is known as the XOR function of H1 and H2, and this is 1 if H1 is not equal to H2 and -1 if H1 equals H2. And what we are required to do is find a potentially multi-layer network, neural network to implement or to classify these data sets D1, D2 and D3. So note that D1 and D2 are linearly separable. So for D1, I can draw a line like this that separates the three plus values from the minus value. The many equations of the line, the one that I will select for illustration is the following rule. Y1 is the sine of H1 plus H2 plus 1.5. So the idea here is that if H1 and H2 are one of the 3 points where at least one value is plus 1, the label is plus. And you can see that this rule correctly implements it. When H1 and H2 are both plus 1, this is positive, the argument, and Y1 is plus, the label is plus. If H1 is plus and H2 is minus, or the other way around, the sum is 0 and the overall value is plus. And if both are minus, then this is minus 2 plus 1.5 and then the label is minus. So this decision rule perfectly classifies the 4 data points in the OR function, and it can be implemented again using a single layer network. So we have 3 values like this. Since we are taking the sine of H1 plus H2 plus 1.5, we'll put the summation block. The bias gets multiplied by 1.5, H1 and H2 get multiplied by 1, and then we pass this through the sine function, and this will be the output. Similarly, note that the data set D2 is also linearly separable. I will draw a line like this, L2, and Y2 hat can be written as the sine of H1 plus H2 minus 1.5. This is an example of a line that separates the or properly classifies the second data set. And again, this can be implemented using a single layer network. Now we multiply the bias term by minus 1.5 and the others by plus 1. We take the sum, we threshold it, and we get Y2 hat. Now, clearly the third data set is not linearly separable. So let's look at it more carefully. Let me zoom that part. And one important difference, however, is that if we draw those two lines we already had, this is line L2, which is H1 plus H2 minus 1.5, and this line L1, which is H1 plus H2 plus 1.5, then the region where Y3 is positive is at the intersection of the two lines. So for L1, the label is positive if you are above L1, and the label is negative here. For L2, our label Y2 is negative here, and it is positive here. So note that Y3, the label should be, for Y3, the label should be positive if and only if Y1 hat is plus 1 and Y2 hat is minus 1, right? So that is the only case where the label is allowed to be positive. So we want to implement basically a network that takes the intersection of these two lines and assigns the value to be plus if the input vector is in the intersection, like in this regions, and it assigns minus everywhere else. And this you can easily convince yourself that one way to do it is to set y3 hat to be the AND of y1 hat and y2 hat with the NOT on top of it. So the idea here is when you take the NOT of y2 hat, this one will be correspond to y2 hat being minus 1, and this one requires y1 hat to be plus 1. So only in that case will the label y3 be positive. In all other cases it will be negative. So this will be plus 1 if y1 hat equals plus and y2 hat is minus, and it is minus 1 in the other cases. So this is what we want, and since we know how to implement the AND function, all we have to do is just combine the outputs and get to the y3 hat. So we now, if we have already implemented y1 hat and y2 hat, then our implementation will involve taking y1 hat, multiplying it by plus 1, taking y2 hat, multiplying it by minus 1, summing them up. We need a bias term. So we'll have y0 hat is 1. It's an AND function, so we multiply by minus 1.5. We sum it up, pass it through the sine function, and we get y3 hat. Now we already know how y1 hat and y2 hat were implemented. They were implemented using this single layer networks. So we can substitute for that. So the final implementation will have h0, h1 and h2. h0 is 1. And then we compute two intermediate values. One is y1 hat, the other is y2 hat. For y1 hat, we just have these connections. This is the y1 hat is the OR function, so this gets multiplied by 1.5, 1 and 1. y2 hat is the AND function of h1 and h2, so this gets multiplied by minus 1.5, 1 and 1, and then we combine this into another AND function from what we have before. So this is minus 1, 1, y0 hat is plus, this gets multiplied by minus 1.5, and this is our final output. So the point here is that we have an input layer, one layer of hidden nodes. This is the hidden layer, and this is the output layer. So a two-layer network implements the XOR function. So again, going back, this particular data set is not linearly separable. D3 is not linearly separable. We cannot draw a single line that will separate all the points perfectly. However, we can express this particular region as an intersection of two lines and then use a two-layer network in order to implement this particular classification rule. Thus, a two-layer network can implement this nonlinear decision boundary, which a single layer network cannot. Now we can take this example a bit further as follows. Suppose that H1 and H2 were outputs of a linear classifier themselves. In other words, suppose there was a H1 was obtained through the following line. It's sine of x1 plus x2 minus 1, and H2 was obtained through sine of minus x1 plus x2 plus 2. So there are two lines. So the input vector is again two-dimensional, x1 and x2, and we have a line that looks like this. It's one here, and the other line looks like this. The intercepts are at 2 and negative 2. And for the first line, this is the region where h1 is plus 1. And this is the region where h1 is minus 1. For the other line, this is the region where h2 is plus 1. And this is the region where h2 is minus 1. And the question asks us to sketch the decision regions for the neural network where y is, say, the XOR of h1 and h2. So what we do is h1 and h2 were not actually directly given to us. They were generated by applying a linear classification rule to an input vector x, and when we apply to using the first boundary, we get the value of h1. If we apply it using the second decision rule, we get h2. And now we want to see that after that, if we apply an XOR function to h1 and h2, what will the corresponding decision regions in the x1, x2 plane look like? So this will be the x1 plane or x1, x2 axis. This is one line. And this is the second line. So this coordinate is 2, this coordinate is minus 2, these are 1, okay? So there are 4 regions here. This is the region where h1 is plus 1, and this is the region where h1 is minus 1. This is the region where h2 is plus 1, and this is the region where h2 is minus 1. So we are taking the XOR of h1 and h2. So in this plane, wherever h1 is equal to h2, the label will be minus. So the output here will be minus. Similarly here, h1 is minus 1 and h2 is minus 1. So the label is minus. And in the other two regions, the label is plus. So if we were to compute the XOR of h1 and h2, this is the decision region we will end up with. For the given input vector x, if it belongs to this region or this region, the label will be minus. In the other two regions, the label will be plus. If we had to implement this decision region in the x1, x2 plane, then we can do that using a 3-layer neural network. So what we will do is, we'll have input values x1 and x2, add a bias term. In the first layer, we will, or actually I won't write the summation now, from now on, that's going to be implicit. So I will just write the sine functions. I will take x0 and I will implement the equation of the first line. So I'll take this, I will apply it by minus 1, and then I'll take the sum of the other two terms. For the second one, I have 2 here, minus 1, and plus 1. So this will be implementing the decision region for L1 and L2. I get H1 and H2 here. I add the bias term. Then I implement the XOR function. So for that, I have to first compute the AND and OR of H1 and H2, like we did before. So I have to basically now implement this neural network on this page. So that will include two layers. So I have to compute y1 hat and y2 hat. So this gets multiplied by 1.5. This gets multiplied by minus 1.5. Okay. And finally, we multiply this with minus 1. Y0 hat is plus 1. This gets multiplied with minus 1.5 to compute the XOR function, and this is the output. So this decision region, this particular implementation will provide a decision region that looks like this. So two parts are minus and two parts are 1. This is clearly a region that cannot be implemented by a single line. So a single neural layer network is not sufficient. A one layer network is not sufficient. But this three layer network implements the above decision region. So this is the input layer. This is the first hidden layer. This is the second hidden layer. And this is the output layer. Okay, so there is a one set of weights between the hidden input layer and the first hidden layer, a second set of weights between the first hidden layer and the second hidden layer, and another set of weights between the second hidden layer and the output layer. That's why there are three. This is called a three-layer neural network. And this network can be used to implement the decision regions like the ones we saw in this particular figure. What if we had more complicated decision regions? So suppose our decision region was looked like this. We are still in two dimensions. And we have one line, L1, like this. We have a second line, L2, that looks like this. And a third line, L3, that looks like this. We want the labels to be plus here, plus here, plus here, and minus everywhere else. So this is my mistake. This should not be there. Okay, so we want to implement this decision rule. Again, using a three-layer neural network. So the key observation is that our decision regions are intersections of planes defined by straight lines. And it turns out that any such region can be implemented using a three-layer network, which is a generalization of the previous example. So to see this, let us look at each of those three lines separately and see how their outputs can be combined to get a decision region like this. So consider, the three lines one at a time. So this is the first line. So this is the case where each one is -1 and each one is +1. This is the second line. And third line is L3. And when we implement this line, H3, now the choice of where H3 is positive and where it is negative is not critical. You can define any one side to have plus and the other side to have minus. That won't change anything. We just arbitrarily select it in this particular fashion. Now what we will do is, for the original decision boundary, suppose we wanted to just implement a decision rule where of the following form. So in the x1, x2 plane, we had those three lines and we wanted the label to be plus here in R1 and minus everywhere else. So we want the output y1 hat to be +1 if and only if x belongs to the region R1. So that is, if you recall what each of these lines are producing, this is h1 is -1 here, so h2 is +1, or this is h3 actually, this is L3, h3 is +1, this is L2, and h2 is +1 as well. So in other words, we can write y1 hat to be the AND of not of h1, h2 and h3. If we had just implemented this decision rule, then we would have a label that would be plus only if x belongs to R1 and it would be minus everywhere else. Similarly, let us look at another decision rule of the following form. We want only this part to be plus and all other regions to be minus. So this is the region R2. So we want y2 hat to be +1 if and only if x belongs to R2. So you can again see easily that R2 will be corresponding to h1 equals +1, h2 equals +1, and h3 equals -1. So we can set y2 hat to be AND of h1, h2 and not of h3 in this example. So we can handle one region where the label is plus using the AND function. If we want the label to be plus only if x belongs to R1, we'll use y1 hat. If we want the label to be plus only when the region is where x is in R2, we can use y2 hat. And similarly, there is one more region, R3, where the label is plus, and that we will take care with the third region, R3. So this is L1, this is L2, and this is L3, and we want this label to be plus, so this is R3, and we want minus everywhere else. So how do we handle this? Well, again, we'll set y3 hat to be plus 1 if and only if the input belongs to R3. So this is the case where L1 gives a plus 1, L3 gives a plus 1, but L2 gives a minus 1. So y3 hat will be the AND of H1, not of H2 and H3. So we can see how each individual regions can be made positive one at a time. But now we want to implement a union of those three regions, and if x belongs to either R1, R2 or R3, we want the label to be plus 1. So this can be done by simply setting y hat to be the OR of y1 hat, y2 hat and y3 hat. So the overall output will be obtained by finally taking the OR function of y1, y2 and y3. So this can be implemented again using a 3-layer neural network. So step 1 is to implement the linear classification rule for L1, L2 and L3. That will give us one layer. Step 2 is to implement the y1 hat, y2 hat and y3 hat. They can be implemented using the AND function. And the final step is to implement a y hat using the OR function.